Why does your phone suddenly drop from 60% to 10% when you step outside in winter? That moment feels like magic, but it's not. It's electrochemistry, physics, and clever safety systems all meeting cold air. In this video, we'll unwrap what happens inside a lithium-ion battery when temperatures fall, why phones sometimes revive when warmed, and what real tricks you can use to keep your device alive on a cold day. We'll use simple analogies so the chemistry becomes intuitive. We'll run small thought experiments you can try, and we'll finish with practical habits that actually work. First, the basic picture. A lithium-ion battery makes electricity by moving lithium ions between two electrodes through a liquid-like medium called the electrolyte. Think of ions as runners in a relay race. The anode and cathode are the two teams' locker rooms, and the electrolyte is the track. At normal temperatures, the runners sprint easily and hand off the baton quickly. Current flows, your screen stays bright, and everything is fine. Lower the temperature and the track becomes sticky. The runners slow down. Chemical reactions at the electrodes also become sluggish. Internal resistance rises. The net effect is that the battery produces less usable current for the same state of charge. Now, a critical piece people often miss. The battery's displayed percentage is a software estimate based on voltage and models of how the battery behaves. When the battery's internal resistance increases in cold, the voltage under load can drop sharply even if there's chemical energy still inside. The phone's protection software sees the voltage fall below a safe threshold and shuts down to prevent damage. So the phone appears to die, but in many cases the energy is still there. It's just temporarily inaccessible. That's why if you warm the device in your hands or pocket, it can jump back up to a higher percentage. The warming lowers internal resistance, voltage recovers, and the device wakes up. To make the intuition stick, imagine a water hose. At normal temperature, the hose is soft and water flows freely. In freezing weather, the hose hardens and narrows, the flow rate drops, and the pressure at the faucet falls. The pump might sense low pressure and cut off to avoid harm. Warming the hose restores flow. A few more mechanics to be precise. Lithium-ion batteries involve multiple microscopic processes: ion diffusion through the electrolyte, charge transfer at electrode surfaces, and movement of electrons through the cell's internal wiring. Temperature affects all of them, but diffusion in the electrolyte is especially sensitive. At low temperatures, the electrolyte becomes more viscous and ion mobility falls off steeply. Some electrode reactions also have activation energy barriers, meaning they need a little thermal energy to proceed quickly. Thus, cold both slows supply and slows the chemical reactions that convert ion movement into useful voltage. There is also a long-term problem. Repeated use at very low state of charge and low temperatures can chemically harm the battery. That's one reason device firmware prevents operation at dangerously low voltages in the cold. The phone is protecting future capacity at the cost of immediate usage. Next, let's talk about capacity versus deliverable power because they are different. A battery has a certain stored energy, like a tank of water, but it also has a limit on how fast it can deliver that energy, like the diameter of the outlet. Cold reduces the outlet size more than the tank capacity, so you may still have energy inside, but you can't draw it fast enough to run a power-hungry CPU and screen. The device then shuts down. This explains why simple tasks like a clock still run, but heavy tasks cause collapse. Now, for concrete tests you can try safely. Take a partly charged phone and place it in a controlled cold environment for a while, like an unheated porch or a fridge set a few degrees above freezing. Watch the battery percentage, then warm the phone in your hands or place it in an inner pocket and observe the percentage jump back. You can repeat this with a thermal camera or a simple thermometer to correlate surface temperature with behavior. Please don't put devices in ovens or near heaters. Overheating is dangerous. These simple experiments make the mechanism obvious. Temperature controls the device's apparent battery life. What about chargers and charging speeds in the cold? Batteries also hate being charged at low temperatures. When lithium ions try to intercalate into electrode materials at low temperature, they may plate as metallic lithium on the anode surface instead of inserting cleanly. That plated lithium can form dendrites, tiny branches that can short the cell permanently. To protect against this, most battery management systems restrict charging below a certain temperature, sometimes allowing only a trickle current or refusing to charge altogether. That's why you might see charging paused, too cold messages. Hardware designers use thermal sensors and control logic to avoid dangerous charging conditions. Now let's explore design remedies that engineers use. Thermal management in modern devices is a balance between weight, efficiency, and cost. Some e-readers and rugged phones include insulation and small heaters to maintain battery temperature. Electric vehicles commonly use active thermal management, fluid loops, and heating elements because battery temperature dramatically affects range and longevity. For phones, passive measures dominate. Careful placement of components for heat sharing, firmware that reduces CPU clocks at low temperature to lower demand, and software that reports conservative battery estimates when environmental conditions deviate from typical. Manufacturers also tune their battery chemistries and electrolyte formulas to perform better at lower temperatures, but chemistry always has trade-offs. Now to the practical part you can use right away. Tip 1. Keep your phone close to your body in cold weather. Your pocket is a tiny incubator and it can keep the device within a safe operating range. Tip 2. Avoid leaving phones in parked cars overnight or exposed on cold surfaces. Tip 3. If your phone dies in the cold, warm it slowly in your hands or an inner pocket before trying to charge. Rapid warming, like placing it on a radiator, risks condensation and moisture damage when you move back into warmer air. Tip 4. Carry a small portable battery in an insulated pouch. If your phone needs external power in the field, warm the power bank and the phone together. Tip 5. Reduce workload in cold weather. Turn down screen brightness, close background apps, and avoid heavy tasks that demand peak current. Lower load lowers voltage droop and can prevent shutdown. Tip 6. If you're about to embark on a long cold outing, charge fully before you go and avoid discharging to very low percentages. Many experts recommend keeping state of charge between 30% and 80% in extreme conditions to reduce stress on batteries. For professionals who operate in cold environments, there are more advanced strategies. Aviation and field equipment include battery warmers, insulating cases, and heated storage boxes. Some specialized batteries use lithium chemistries optimized for low temperature with alternative electrolytes that maintain ion mobility better, though such cells typically have lower energy density or higher cost. Let's address a common myth. Cold permanently reduces capacity. The truth is nuanced. Short-term cold exposure mostly reduces deliverable power and apparent capacity. Once warmed, most of that capacity returns. However, repeated cycling at low temperatures or charging while cold can cause irreversible damage like lithium plating and structural changes in electrodes. So occasional cold use is usually fine, but repeated abuse shortens service life. Finally, why does this matter beyond convenience? Understanding reveals the trade-offs designers face and explains why device manuals recommend certain temperatures. It also empowers you to make better choices. Simple habits extend useful life and avoid frustrating shutdowns. The bigger lesson is general. Batteries are chemical devices that trade off power, energy, cost, weight, and safety. Temperature is one of the knobs that shifts those trade-offs dramatically. To wrap up with a neat conceptual moment, remember the relay race. When the track is sticky, the team slows. The software that reads the scoreboard sees the slowdown and calls a timeout to protect the runners. Your warm pocket serves as the friendly stadium mechanic who sprays the track and gets the race moving again. If this explanation made the next winter outing less mysterious, you can try the pocket warming trick the next time you head out. If you found this useful, press like, share with a friend who lives somewhere cold, and subscribe to how it actually works. We break down everyday mysteries into simple mechanics you can use. Keep your devices warm, keep your curiosity warmer, and I'll see you in the next video.